Okay, so we're finishing this material today, and of course, Wednesday and Friday, we actually gonna start multivariate regression. Um, you remember this material actually centered on multivariate analysis of variance. I've already walked you through one way multivariate analysis of variance, and of course, I remember. I also walk you through how to do that now. You can see what I'm displaying now. Okay. Um, when I have four dependent variables, and of course I'm looking at the effect of cylinder. Okay, I'm looking at the effect of cylinder. We have six cylinder, eight cylinder, and so on like that. We're looking at the effect of categorical variable cylinder on the fuel efficiency of a car, okay, the DISP, the horsepower, and the weight, okay. And of course, if you take a look at what I have, we got different kinds of tests that we can use, in multivariate, one-way multivariate analysis of variance. Here, I use a pillar test statistics. I use a wiki lambda statistic. I use a Roy test statistic, and I use Otelin only test. And of course, you can see the p-value associated with each of that. It's less than 0.05, which indicates, um, significance. Now, after that, I want to go to variance of treatment effect difference. You know, when I talk about variance of treatment effect or difference, when I say treatment effect or difference, if I were to measure the effect or treatment effect difference, I actually need the variance of it. Okay, because with that I'll be able to tell about precision, okay, and reliability. Okay, so if finding the variance of treatment effect difference, okay, this will enable us to conduct different kind of tests. Maybe for instance, we actually want to conduct a pairwise comparison test after the null hypothesis has been rejected in the multivariate analysis of variance, or we actually want to construct confidence interval, okay, or we want to investigate whether there's a quality of covariance structure among groups. Now, the treatment effect is defined as that guy, as you can see. Okay, the alpha cap kj equal that minus that. We got two different means here. Of course, I think I've given you the definition of what the two means represent. The S bar kj is the kth group mean for the jth variable. Okay, then X bar j is the overall mean of the jth variable. Don't forget, we got so many variables, okay, so many dependent variable. We may want to look at the overall mean of a particular dependent variable. We may also look at the kth group mean, okay, for the kth variable, okay. Now, uh, so like I said, if I want to measure, the effect, I need the variance of the effect difference. If I want to measure the treatment, the difference of treatment or effect, I need the variance. The variance is actually this. Okay, the variance is that. Let me tell you this. Whenever I want to investigate an effect, I need the variance of that effect. Just like I want to tell how reliable is an estimator, I need the variance of an estimator. Because if I'm able to get the variance of that effect, that will enable me to conduct statistical inference. Conducting statistical inference, I need the variance of that particular effect. Now, if you take a look at what I have here, the sigma jj will be the j diagonal of the variance covariance matrix, which should be the variances. Okay. Now, with that, we can actually formulate a simultaneous confidence interval. Why am I looking for confidence interval? I'm actually want to conduct a simultaneous confidence interval probably because the null hypothesis has been rejected in the multivariate analysis of variance. I want to know where the difference lies. Okay. Now, this is the formula. The variance of that equal to that. Okay. Using the Benferroni. Don't forget the idea behind Benferroni is to control the family-wise error rate. If I have so many if a number of tests increases, the type 1 error rate increases. And of course, the Benferroni will enable us to control for that. We don't want situation whereby um the probability of type 1 error will be inflated. But let me tell you this. We have a way to investigate all of that in R. In this course, I allow the use of R software. Okay. Now, if you take a look at what I'm displaying now, is least square MANOVA means in R. What do we mean by that? What we mean by this is, can we have a way to adjust means that we have controlling covariates? I'm going to say that again. Can we have a way to adjust the means controlling covariates? When I say controlling covariate, is controlling or predictor that could have effects on what we're doing. Okay. So, and that is what we call, adjusted means. Now, I need you to pay attention now. Okay. You know, if we are controlling predictor one, for instance, let's say we identify a particular covariate or predictor that we want to identify, control. Now, what I'm trying to tell the world is that the adjusted mean for four-cylinder vehicle, six-cylinder vehicle, and eight-cylinder vehicle is that. Now, I'm actually I'm getting this for what now? For weights. Don't forget, we got so many dependent variable. We're looking at the effect of cylinder on different, on so many dependent variable like horsepower, weight. Okay, for weight now, if you take a look at this, I'm at WTS, I'm talking about weight. Okay, can we have a way to find the adjusted mean, okay, for the response variable weight, putting into consideration the level of the categorical factor? What is the level? What is a categorical factor? Cylinder. We're looking at the effect of four-cylinder engine, six-cylinder engine, eight-cylinder engine. We're looking at the effect of that on the response variable. But right now, we're focusing on weight. Look at that, WTS, weight. So here, we are actually giving the means, these are the adjusted means. Okay, what you see here is the adjusted means. This is the corresponding standard error. Okay, and of course, these are the confidence interval. I want to take note of that. Now, if we actually control for another predictor, okay, this is what I'm actually going to have. Controlling for another predictor now is actually telling us the covariance structure, the standard error here is higher than than the one here. If you take a look at that, at each cylinder, the standard error when I'm controlling predictor number three, predictor three, okay, is higher than when I'm controlling predictor one. Okay, I wanted to take note of that. When the standard error is very high, of course, you expect to have a wider range of the confidence interval. Of course, if you compare the confidence interval there with the one there, so what determines the confidence interval is actually the standard error. And the standard error here is the square root of the variance that I talked about the other time. Okay? Now, if you want to look at it from this angle now, please pay attention. I want to maybe I've conducted multivariate analysis of variance where I've simultaneously looked at the effects of cylinder. I'm looking at the effect of cylinder on multiple dependent variables. The multiple dependent variables, number one, MPG, which is going to measure the fuel efficiency of a car. Then HP, the horsepower, HP, the horsepower, okay, and so on like that. There are so many, okay, but I actually want you to see the code, the Bonferroni correction for the dependent variable. Now, when the dependent variable is MPG, please pay attention. When I conduct multivariate analysis of variance one way and the null hypothesis is rejected, then it means there's a difference in the means. Okay. Now, I don't know whether in the means of this dependent variable or that dependent variable or the other dependent variable. If I really want to know, I will need to conduct a separate analysis based on the dependent variable. Now, right now, I want to construct a Benferroni pairwise. What do we say Benferroni pairwise? We actually want to identify where the difference lies. We have rejected the non-hypothesis, but right now, we're looking at the situation, we're looking at the dependent variable MPG. Now, please pay attention. Take a look at this. We want to see different exists in the fuel efficiency of three different cylinders. Four engine cylinder, six-cylinder engine, eight-cylinder engine. We will now want to know where the difference lies. Okay, where the difference lies, don't forget the dependent variable is fuel efficiency. When there is a difference that exists, does it exist between four-cylinder and six-cylinder? How am I going to know? I will look at the lower bound and the upper bound. If zero lies, there's no difference. But here zero doesn't lie. Yeah, from positive to positive, zero don't lie. Negative to negative, zero don't lie. It means, okay, the difference that exists is between four-cylinder and six-cylinder. Does that make sense? Now, when you look at the second one, 4 and 8, difference also exists. Okay, but when you look at 6 and 8, because 6 and 8 is from negative lower confidence interval to positive upper, zero lies in, which means difference does not lie between 6-cylinder and 8-cylinder. Is there any question? Now, conducting Benferroni pairwise confidence interval will enable us to identify where the difference lies. But right now, what are we focusing on? We're focusing on one dependent variable at a time. Now, I want to go to another dependent variable. This time around, I actually want to go to the horsepower, HP. Okay, now I want to look at that again. Okay, here now. So what do you see? If you take a look at what I'm having right now, I think the difference actually lies here and here. Because negative to negative, there's no zero in the interval. But when you look at the first one, okay, you can see. Now, you're actually going to perform the Befferoni pairwise confidence interval. You have to perform that in each dependent variable. Any question on this? Any question? Like I said, I need you to ask question. I want the performance and the midterm too, the median or the mean to be 99%. So please ask question in case you don't understand. Now, I want to move right now. Now, let me tell you this. Before a court can entertain a case, that particular court must have a territorial jurisdiction before we can use multivariate analysis of variance to conduct whether multiple vector means are the same or not across group, there are assumptions that need to be met. And one of the assumptions is that we should have across group, the covariance structure have to be the same. Okay? The covariance structure have to be the same. If the covariance structure are not the same, that could invalidate whatever assumption, whatever decision that you're going to take, using the multivariate analysis of variance. And because of that, before we embark on the test at all, the very first thing is to investigate that. Now we call that testing the homogeneity of covariances. Okay. Now in the testing of that, we actually want to see whether the covariances are the same across groups. Now, this is going to be the null hypothesis, the HO, and this is the alternative. Now, what is the appropriate test? The appropriate test is the likelihood ratio test that's centered on wiki lambda. Take a look at that. Now, can I explain this one here? What is SK? What is you're actually going to see? I'm finding the determinant of SK. I'm also finding the determinant of XP. The two of them are sample covariances. Okay. But you know what? How am I going to get SP? How am I going to get SK? Now, I'm going to start with the SP. Please pay attention. Okay, if I want to start with the SP, I need to know W matrix. The W matrix is sum of square product within that we did in the multivariate analysis of variance test the other time. Okay, and of course, the SK is the sample covariance for a particular, for a particular variable. Okay, now if you take a look at what I have, okay, the test according to Judge Boss follow this. Okay, the moment I get my, lambda here, I'm going to do -2 times that. Then I'm going to compare with this to take a decision. U is this guy here. Can you see U? Okay, P is the number of variables, the number of dependent variable. G is the numbers of groups that we want to compare. N is the number of observation. NK, the number of observation, okay, within K's variable. I needed to take note of that. Now, and after that, then we can take a decision. But you know what? Don't be scared. We have a way to do that in R. Look at this. This is how to do that in R. It is called box M test. Box M test. Okay. Now, the box M X. What is my X represent? I'm going to go back. I wanted to see what my X. Please pay attention. I want to show you what my X represent. Now, can you pay attention to this in the code? Can you see what my X represent? The multiple dependent variables. My X represent multiple dependent variables. Can you see that? Multiple dependent variables. And you can see the cylinder. Cylinder is the categorical factor. We're looking at the effect of categorical factor on multiple dependent variables. Now, I needed to pay attention. So in the box M test, I needed to see what we're doing. Now you know what X represent. Okay, you know what X represent. Now, X that you see here represent the multiple dependent variable. And of course, cylinder is a categorical factor that we're looking at effect. And of course, After that, take a look. Oh my God. Look at the p-value here. When the p-value is less than 0.05, then it means you need to reject the null hypothesis. Rejecting the null hypothesis, mean when you conduct a multivariate analysis of variant test, whatever decision you take is declared null and void because there's a violation of assumption. Let me tell you this. What makes a model to be great is when assumption hold. Okay? Assumption is what make model to be great. If there's a violation of assumption, we cannot trust our model. And that is the reason why the test of homogeneity of covariances is very, very crucial before conducting multivariate analysis of variance tests. Is there any question? But let me tell you this, it was argued by some statisticians that N tests, that is multivariate analysis of variance tests, is sensitive to non-normality. So it may be okay to proceed with the MANOVA in some cases when M-test rejects the non-hypothesis. But assumptions of normality is different from assumptions of constant variance. Assumptions of constant covariance matrices is very, very crucial. Okay, now I want to welcome you to the last, subtopic in this material. I want to welcome you to two-way multivariate analysis of variance, the one we just completed, the one we started before the spring break and we just completed now. It's actually based on just one single categorical factor. You are testing the effect of one single categorical factor on multiple dependent variables. But what if in a situation where we got more than one categorical factor? I think I gave you an example the other time when I was talking about the effects of gender and extracurriculum activity, okay, on the exam performance of the students. Gender is one factor, extracurriculum activity is another factor. They both have levels. Then if I actually want to conduct a test, I'm never going to do multivariate one-way multivariate anymore. It's going to be two-way multivariate. Why two-way? Because I got two categorical factor. But before you can understand the multivariate analysis of variance involving two categorical factors, I need to first walk you through the univariate. Because if you understand the univariate, if you have a recap on the univariate, we're actually going to generalize the univariate to multivariate situation. Now, I need you to pay attention, okay? Now, this is what I'm trying to show. Case right now is when we have a univariate, like univariate means I have one dependent variable, just one, but I'm looking at the effect of two categorical factors. Okay, now this is the model. In exam, I can ask you to state a model. What is the model for one way? What is the model for two way? Now, this is a model for two-way univariate analysis. Okay, we have the treatment effect. You can see there are two treatment effects here because we have two categorical factor. And that was why I said factor one and factor two. Alpha K factor one, alpha beta A factor two. Take a look at that. Okay, this is the overall mean. Okay, and this guy here, because when I have two factors, there's possibility of interaction. Do you know that if I'm looking at the effect of extracurriculum activity, when I talk about extracurriculum activity, okay, for instance, if I'm looking at effects of gender. Okay, gender, I mean male, female, gender. Okay, effect of gender. Okay, this is going to be factor one, effect of gender and extra curriculum, extracurriculum activity. And when I talk about extracurriculum activity, maybe somebody is in a music group, sports, or debate in a school. Okay, on academic performances. Academic performances are probably in maths, science, and reading. Math, science, and reading. Now, look at this. The math, science, reading, there are multiple dependent variables. This is the two-factor gender one extra curriculum. This is factor two. If I want to investigate this now, I need a multivariate. I need a two-way multivariate. But you know what I'm doing right now? I first want to start with just one way. What is going to make this to be one way if I'm looking at the effect of this and this on just maybe performance in math only. Does that make sense? Okay, now this is the model. When you are writing a model, I can ask you to explain what each term represents in the model. Okay, now you know what I'm trying to say here? I have a treatment effect factor one, treatment beta F factor two. This guy's interaction. Whenever you have two factor, there's possibility of interaction. Now, interaction effect is going to be, when interaction effect is significant, you know what I mean? Maybe effect of gender on the academic performance may depend on extracurriculum activity. Situation where effect of a categorical factor on a response depends on another categorical factor, we need an interaction effect. We can have a two-way with an interaction effect. We can have a two-way ANOVA without interaction effect. Now, take a look at that. And of course, the error time follow normal distribution, okay, with the mean equal to 0 variance sigma squared. Now, I need you to pay attention in a univariate ANOVA. In ANOVA in general, ANOVA analysis of variance has to do with the breaking down of the total sources of variation into various components. Now I have SLKI, this particular, I want to break it down. Okay, looking into the model. Don't forget, when I wrote the model the other time, look at the model. This guy is being decomposed into this, and that. If I have a data inside, I needed to pay attention. Data is being broken into sample mean. This is to give you an opportunity to see what we mean by treatment effect. The treatment effect is subtracting the overall mean from the group mean. Take a look at that. Then this is for factor one, factor two interaction, and this is for the error. And of course, all of this is how you're going to get each of that. Okay. Now, whenever that, oh my God, whenever the decomposition of a response variable is involved, there's also going to be a decomposition of the total sources of variation associated with that particular response variable. Now, if you take a look at this guy here, SS total, you know what I mean? That is the total variation around the response variable. Maybe total variation around the performance in maths. Does that make sense? Total variation around the performance in maths. What we're trying to say, total variation around the performance in maths can be broken down into variation explained by gender, if factor A is gender, and explained by extracurriculum activity, which I call SSB, and explained by interaction, which I call SSAB, and the error. The error here is unexplained variation. Unexplained explain variation. So SSA, SSB, SSAB, they are collectively called explained variation. So the total variation can be broken down into explained and unexplained. Does that make sense? Okay. Now with that, we'll be able to form an ANOVA table. Okay. With that, we'll be able to form an ANOVA table. Okay. We're going to have factor one, factor two, the interaction, the error. They're going to have the degree of freedom. We're also going to have a way to find the sum of square. You've done this in the lower level statistics, particularly in experimental design. Okay. Now, this is, you're actually going to have so many hypotheses you want to test. You want to test hypotheses about factor A. You want to test hypothesis about factor B. You want to test hypothesis about interaction. But you know what? We actually want to extend this to multivariate version. Okay, extending this to multivariate version right now is that we are no longer going to have just one dependent variable. We actually want to have more than one dependent variable, but we are still retaining two categorical factors. Is there anyone in this class who doesn't understand the way I talk? Anyone who doesn't understand the way I talk? You know, you have 100% right to challenge whoever that is teaching you, respectfully, like oh, because you pay for the service, because I'm actually going to get paid at the end of the day. So if you know you get stuck, I think let me also say this. Sometimes I have issue with Zoom, but right now I think I've talked to the technical department in the Zoom, and they've addressed that. You can visit with me during my office hour without any inch now. So my office hour is conducted remotely. In case you get stuck, I need you to reach out. I just want to hear from you. Now, you know what I want to do right now? I want to extend univariate and two-way univariate and over to multivariate. But I need you to see the way I wrote the model right now. The model is now in terms of vectors. If you take a look at, let me show you. I'm quickly going to go back to the univariate model. Okay. Please pay attention. Take a look at this. The way this guy is written now. Okay. They're actually going to look the same, except that they may not necessarily be they're actually going to be vector. And the decomposition, look at the decomposition, stay the same, okay? But you're actually going to see the way you're going to write the ANOVA table. The other time, this was not written in matrix like this, where you have this transpose. Do you know what you have here in factor one? You have this one squared. I'm going to take you back to univariate. Please pay attention. You're actually going to see, oh my God, you see that guy squared? But in the multivariate now, I'm going to write this. I'm going to say that times the transpose because we're now talking about multivariate case. I'm going to do the same thing for this guy, for that guy, and I needed to compare the two. Okay, so take a look at what I have now. Can you see that now? Guess what I have right now? And you know what this guy is trying to say? Sum of square products. Okay, for total variation can be broken down into each of that. Just like what I said the other time. Okay, now what are we testing? Like I said, we're going to test three things for factor A, for factor B, and for the interaction. Don't forget interaction between A and B. Now, how do we test? This is where I need you to pay attention in case I want you to write formula in the exam. Please pay attention. Now, you need to first find this guy. When you take a look at that guy, the numerator is sum of square product for error. The denominator is sum of square product for factor A plus sum of square product for error. If I want to talk about factor A, if you look at the other one, and if you take a look at that, This is my test statistic. My test statistic. Whatever I go here, I'm going to take the log multiplied by VA. Now I will compare with this chi-square. I'm going to check from chi-square table. I will reject H naught if this guy is greater than that. Okay. And what is some of you may be wondering, what is my VA? This is the VA. Okay. Then I'm gonna take this, I'm gonna use the same for factor B. What is the difference between that? It's just this guy here representing that of A and this guy representing that of, look at that. That is different. In each of them, the numerator is sum of square product for error. Sum of square product for error. Look at that. Now, what about the interaction? Okay, what about the interaction? Okay, what about the interaction? Take a look at that for interaction. Now, this is for the interaction. Can you see that? For the interaction, so whether for factor A or factor B, oh, give me 1 second, I'm gonna do something now. Oh my God, you're gonna see something now. Okay, now whether whether for whether for whether for A or for B or for C, there is something that is common to all of them, the numerator. I see the numerator is the determinant of sum of square product for error. But the denominator also going to have sum of square product for error plus the sum of square product of the factor you are testing for. Does that make sense? Take a look at that. It's easy as that. Now, you see how you can take a decision now about this. And after taking your decision, what is going to happen? Now, this is the R, if you want to do that in R. Now, I still want to retain the example that I used the other time. The other time, please, I need you to pay attention. The other time, you know what we did? We look at the effect of cylinder on multiple dependent variables. But right now, we are adding another factor called transmission. What is the effect of transmission? Of course, everybody know in a car, we have transmission, right? What is the effect of transmission and cylinder, okay, on MPG of a car, the fuel efficiency, and so on like that? Okay. Now now the wiki we can use wiki lambda again to test. Oh my God! If you take a look at this guy now, what is that? That is two-way multivariate analysis of variance with wiki lambda. What do you see? This gives me opportunity to take a decision for cylinder, for cylinder. Having 2 degrees of freedom for cylinder means there are 3 levels of cylinder. Having one degree of freedom transmission means we got 2 levels of transmissions. What is happening here is telling us significant, significant. But what about the interaction between them? The interaction is not significant. Can you see that? With this, you know, see that? The p-value is greater than 0.05. Take a look at that. This is easy way. This is doing it in R. Okay. Now, the next thing I want to talk about right now, the next is because the interaction is not significant. When interaction of 2 factors is not significant, what is trying to tell me here, the effect of cylinder on those multiple dependent variable does not depend on transmission, or effect of transmission or multiple dependent variable does not depend on cylinder. And that is why you see the interaction, not being significant, which means I can run a new module where I'm actually going to exclude interaction. Oh my God, this is the new module now without interaction. Look at the new module that I'm feeding. Okay, in that one, I'm only going to write ln x on transmission plus, I mean cylinder plus transmission if I don't want interaction. But the one with the interaction, I need you to see the difference in the code. Look at the difference in the code. You're actually gonna see, oh my God, look at what I'm saying here. The difference in the code is that here you're multiplying. When you're multiplying the two categorical factor, you are telling R to include interaction. If you are adding the categorical factors, you are telling her you don't need interaction. Does that make sense? Okay. Now, if that is taken, now the next thing that we want to do now is to also adjust for means. Okay, adjusting for means. Okay, that we did that in multivariate one way. We also want to do that in multivariate two way. Okay, this is the code. Okay, this is the one for cylinder, and this is the one for transmission effect. Don't forget, this time around, you got two categorical, and if you want to construct Bonferroni where you actually, because the factor is significant, the cylinder is significant, the effect of cylinder on the multiple dependent variable is significant, effect of transmission is significant. It is better we actually construct a Bufferoni pairwise confidence interval to be able to know where the difference lies. Now, right now, I want to know where the difference lies. Okay, I'm on the cylinder. Okay, please take a look at this. I'm doing this for the MPG. I told you you're going to do that for one dependent variable at a time. So take a look at this. So the difference here is between this guy and this guy because of the fact that you have the lower and the upper band positive, positive. It is not between cis cylinder and A because negative to positive includes zero. Now I'm only doing that for MPG here. Then cylinder, they're also going to do that for transmission. Don't forget, you got two categorical factor. Now, can somebody tell me why is it that we only have one comparison on that transmission? Can somebody tell me why we only compare? Why do we have only one pairwise comparison? Because we only have two levels. Send me a message for extra credit. Now, let me tell you this. You've seen your midterm one result. For those of you who have earned extra credits, I need you to send me a message. You advise me whether you want to spend your extra credit on this midterm or you want to save it for the next exam. Does that make sense? You send me a message for that. Okay, you know what? This is doing it for MPG. You're also going to do it for other dependent variables. Okay, now what next do I have? What next do I have? What next do I have? Okay, you know what? That is the end of this chapter. On Wednesday, I'm going to start a new topic called multivariate or regression. And let me tell you what is going to be in the midterm two. In the midterm two, we're actually going to have, uh, you know, hypothesis testing that involve hypothesis testing and confidence interval involving a single vector, two vector means, multiple vector means, okay, all the way to what we want to start on Wednesday, okay, all the way to multivariate regression. So which means in the midterm too, okay, we're actually going to revolve, the question will revolve around what we started, this particular material that we just finished and the material that we're starting Wednesday that we're likely going to finish on Friday. But before the end of the week, I'm also going to upload the midterm two practice question. Before I go, make sure you attend my lecture regularly. And if you watch my recordings, come to my office hour. If you get stuck, like I said, you have the 100% right. okay, for this service, to ask questions, to challenge whoever that come before you. Okay, any question before I go? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone. Okay, so in case you have not, your booklet is here. Okay, and if I make mistake in addition, please let me know probably on Wednesday. Okay, the booklet are there.